Okay, so we're back and we're going to try to produce the second video. Hopefully, the first video seemed to be okay. Hopefully, this second video will have no audio issues either. So we've gone through Descartes' rule of signs, we've gone through the potential rational zeros theorem, and we've gone through the factor theorem. And we've put all that together to write out the factored form of a polynomial in example 5. We're going to apply that one more time here in example 6. This one's an entirely new problem, so we're not building off anything that we've already done. So we're going to do it step by step. First, we're going to start off with Descartes' rule of sign to find the possible number of positive real zeros that this function may have. So let me just write here positive real zeros. And let's count our sign changes. So we go from positive to negative is 1, negative to positive is 2, positive to negative is 3, negative to positive is 4, positive to negative is 5. So this has 5 sign changes in the original function. So that means that our positive real zeros could be 5, 3, or 1. Remember, we just keep reducing by 2 until we can't reduce it any further. Now let's evaluate the function at negative x. This would be a whole lot better if I could just sit here and work on this with you guys and not have to write this out and have all this dead air silence. I'm not enjoying this. All right, so we evaluate it. We get negative x to the 5th. All right, so we have 0 sign changes. So the negative real zeros for this particular function are 0. Because when we evaluated at negative x, we came up with no sign changes. So that's going to make this nice when we look at the potential rational zeros theorem on this one. Remember, potential rational zeros, we look at the values for p, which is our constant at the end of the polynomial, and we look at the values for q, which is our coefficient at the beginning of the polynomial. In this case, q is 1, so we don't have to worry about doing any of the division because everything divided by 1 is going to be itself. Also, based off Descartes' rule of signs, we know that we only have positive real zeros, so we can ignore all the negative factors of 36. So that simply means all we need to do is list the factors of positive 36 without worrying about any of the negative values, because by Descartes' rule of signs, we only have positive real zeros. We found that we have no negative real zeros. So all the factors of 36 are 1, 2, 3, 4, 6, 9, 12, 18, 36. I think that's all of them. Yeah. All right, so we're going to start using these values, and we're going to use the factor theorem. So we take one of these numbers and we evaluate the function. So if we take 1, that's our first factor or first number listed. So we evaluate the function at 1. We do end up with 0, I believe. So we have 1 to the 5th minus 7. All right, and when we evaluate this, 1 minus 7 plus 19. All right, that does equal 0. All right, so we did find that 1 works, so this means that we have found our first factor, which is x minus 1. So I'm going to highlight that, and we'll keep going. So we found 1 to be a 0 of the polynomial. So let's take that 1 and let's do our synthetic division. Remember, we want to try to find a depressed equation. We're starting out with a 5th degree polynomial. So even a 4th degree is not going to be the easiest thing in the world to factor, but let's go ahead and depress this down to a 4th degree polynomial. So the coefficients on our original function are 1, -7, 19, -37, 60, and -36. So remember, our 1 comes straight down. 1 times 1 is 1. We add these together. 1 times -6, add them together. 1 times 13, add them together. 1 times -24, we add these together. 1 times 36, and we get 0. So our depressed equation, we started out with x to the 5th, so now it starts out at x cubed. And we have the new polynomial x to the 4th minus 6x cubed plus 13x squared minus 24x plus 36. And if you'll notice that the constant at the end of this one is still a positive 36, so the same potential rational zeros exist. The list hasn't changed. So we're going to try another value here. If we tried 1, we would find that it doesn't equal 0. If we tried 2, we find that it doesn't equal 0. If we tried 3, by substituting it into the original function is what I mean to say, then we find that it does equal 0. So what that tells us then is that x minus 3 is another factor of this polynomial, and we're going to depress it even further. So we're going to do the synthetic division, except this time we're using the coefficients from our depressed equation. So we have 1, -6, 13, -24, and 36. Bring the 1 down. 3 times 1 is 3. 3 times -3 is -9. 3 times 4 is 12. 3 times -12 is -36, and we get a remainder of 0. So now we have a new depressed equation. We started with a 4th degree, so now we're down to a 3rd degree. So we get x cubed minus 3x squared plus 4x minus 12. And what's nice about this, yes, it is a cubic function, but if you pay attention, you can notice that this does factor by grouping. So we can actually group these terms and do our factoring. And what we'll end up with is we can factor an x squared out of the first 2 terms. And we can factor a 4 out of the last 2 terms. And it gives us this factored form, x squared plus 4 and x minus 3. So we found the remaining 2 factors of this polynomial. If we put all that together, we have the x minus 1, that was our first factor that we found. We have the x minus 3, which was our second factor. And then we have this x squared plus 4. And we have x minus 3 again. Well, instead of writing x minus 3 again, we can just square the current x minus 3 that we have. So this is the factored form of the polynomial that we started with. And we can also convert all of these to zeros. The first one being 1, the second one being 3. And then the third one is a complex 0. So we don't list it because we're only talking about real zeros right now. And then example 7 ties back into what we just did. Find the real solutions of the equation. And that's just going to be those values 1 and 3 that we just found. The x squared plus 4, if you don't believe me about it having a complex 0 as a solution, when we subtract 4 from both sides, then we take the square root. We have the square root of -4. Anytime you take the square root of a negative number, you are generating a complex solution. So we will ignore complex solutions for right now. All right, moving on with our next example. And this is where we start talking about the the bounds on zeros. And the bounds on zeros is not anything difficult to understand. It's just tedious to work with. We want to come up with a way of finding the zeros, or a limiting factor, I should say, on the zeros of a polynomial to maybe give us something to work with to narrow down a large list of potential rational zeros. So the example that we see here in number 8 is identical to what we had in example 4. So we're going to go ahead, I'll write down the potential rational zeros one more time for this one so that you don't have to go back through your papers and find where we were at. Okay, so there's the potential rational zeros, and sometimes you'll end up with a list of a much larger list of potential rational zeros, and you don't want to go through and test every single value. So what the bounds on zeros gives us, what that theorem gives us, is it kind of narrows this list down to a range of values that we may want to look at. And here's how it works. You pick the first. We're only dealing with integers too, so you can ignore the 1/2 and the 3/2 for this particular process. You start out with the smallest positive integer value in your list. So in this case, it happens to be 1. And then we're going to do synthetic division with our original function. So 2, 11, -7, and -6. When we do the synthetic division, this is the third line is all we're interested in. We're not even interested in the value so much unless there's 0. You look at that third line. If the third line has all positive values or 0 values, then you have found an upper bound for your zeros on the function. So when we used 1, which was our smallest integer value from the list, we found all positives or zeros in the third line of the synthetic division. So that means that we have found an upper bound on the zeros of the function. And that upper bound will happen to be 1 because that's what we used for the synthetic division. So we don't have to do anything else for the upper bound. Once you find a third row in the synthetic division that is all positives or zeros, you have found the upper bound. So then now we have to find that lower bound, and the lower bound is doing just the opposite. We go in the negative direction. So our first negative value is -1, and we do the synthetic division. But in this case, we're not looking for all positive values. We're looking for alternating signs or zeros. So we will do the same thing, coefficients. And then now we will do the synthetic division. And here we can see a positive, positive, negative, positive. Those signs don't alternate, so we're going to go to the next value, which would be -2. And we're going to do the synthetic division again. Positive, positive, negative, positive. Again, we don't have alternating signs, and we can keep going through until we get to the very last integer value, which is -6. And even when we try -6, it still doesn't work. So what does that mean? What do we do at that point? We haven't found a lower bound. Just because the number is not in your list doesn't mean you can't keep trying. So once we get to -6, which is the last negative integer value that we have, we go on to -7, and I'm skipping 3, 4, 5, and 3 and 6 just to try to keep the video shorter. It's still the same process. But when we try -7, we have -11, -7, -6. We do the synthetic division. Okay, so here we notice positive, negative, positive, negative. We have alternating signs. Because we have alternating signs or zeros on this one, we have found our lower bound for our zeros of the function. And this gives us a lower bound of 7, negative 7, I should say. So now we know that the bounds on the zeros for this particular function lie somewhere between negative 7 and positive 1. And that helps us. Well, it didn't really help us so much in this particular list because all of our values happen to be between negative 7 and positive 1. But if we had a much larger list, then we would know that we could eliminate anything that was less than negative 7, and we could eliminate anything that's greater than positive 1, and we wouldn't erroneously test those values and waste our time. The intermediate value theorem is going to be the last thing that we talk about. We're going to look at two examples here. With the intermediate value theorem, it just simply says that if we evaluate a function at two values, if the sign is different on the evaluation of those two particular values for x, then somewhere between them there has to exist a zero of the function. So what it's saying is if we go from positive to negative, then that graph would somewhere cross the x-axis between that positive value and that negative value. And the same is true if we go from negative to positive. So all you're doing is evaluating a function. And if you find two opposite signs when you're in your evaluation, then you know that a zero exists between those two numbers. And we're going to do that with example 9 and example 10. They're going to build upon one another here. So example 9 just says show that the function has a zero between 1 and 2. So let's evaluate it at 1. And what we get is 1 minus 1 minus 1. And that's going to be equal to negative 1. All we're interested in is a sign. Then we do it for positive 2. So we have 2 to the 5th minus 2 cubed minus 1. It's going to be 32 minus 8 minus 1, which is 23. So we've gone from negative to positive. And so that shows right there that there has to be a zero between those two numbers. With example 10, we're going to see how we can kind of narrow that down algebraically without actually having to graph the function. If they're both negative, then the graph doesn't cross the x-axis between the two values. If they're both positive, the same thing is true. It doesn't cross the x-axis. So what we're going to do with example 10 is actually kind of narrow it down to two decimal places. We've already established that a zero exists between 1 and 2. So let's take that interval from 1 to 2 and divide it up into 10 equal intervals. So now we're looking at 1 to 1.1, 1.1 to 1.2, 1.2 to 1.3, and we can keep going until we get to 1.9 to 2. And what that's done is taken our intervals and brought it down to a 1 decimal place. We'll have to do this step again to get it down to 2 decimal places. But we're going to do the same thing. We're going to test these intervals and find where does the sign change. Well, from 1 to 1.1, I've already done these. It ends up being negative to negative, so there's no sign change. From 1.1 to 1.2, they both end up being negative, so there's no sign change. But what happens when we look at 1.2, when we evaluate the function? It's negative 0.23968. And when I evaluate it at 1.3, I get 0.51593. So somewhere between 1.2 and 1.3, the graph crosses the x-axis because we've gone from a negative value to a positive value. There is a distinct sign change there. So now let's take that interval 1.2 to 1.3 and break it up into 10 intervals. So now we're adding another decimal place. So we go 1.2 to 1.21, 1.21 to 1.22, 1.22 to 1.23, and we'll keep going until we get to 1.29 to 1.30. Again, we test these values, 1.2 to 1.21, it's negative, negative. 1.21 to 1.22, negative, negative. And all the way up until we get to 1.23, which is negative 0.04555613, and 1.24, which is going to be a positive number, 0.25001. So somewhere between 1.23 and 1.24, we have a zero of this function. And we always just look at the lower bound. So we can say with a strong degree of certainty that 1.23 is a zero. I should say an approximate zero of the function. I think I only have 2 questions like this on the assignment, so this is just to get you to practice. This is more about gaining mathematical understanding about what's going on. Like I may have mentioned in the first video, I realize you guys can graph every single one of these and find the zeros, but you do also want to make sure you understand why those zeros or where they're located and how you come up with them. It's one thing to blindly trust a calculator. It's a whole other thing to actually understand what you're doing. Like I said, I realize that both of these videos will probably generate several questions, and I am anticipating that fact. So tomorrow we will meet for a Zoom class, and I'll address every question that you guys have on 3.1 and anything here from 3.2. Hope you guys are doing great, and I can't wait to see you tomorrow.